Hello and welcome to week 6 sentiment analysis. This is where it starts to get fun. So, as always, we recap a little. So, homework 4 showed us that, words can be numbers, words can be vectors. Homework 5, we kind of pulled order, information, knowledge out of sentences. Well, now week 6 shows them what happens when we take these words and we scale up to big prompts, to words, to text, to something bigger. I just made that a little bit bigger for you. That. Man, my mouse is just jumpy today. So, sentiment analysis is maybe not necessarily the starting point of an LLM, but you have this idea where now we can understand human emotion, human intent, human relations. We can understand intent. And I guess that's really the starting point of it. And we're not really looking at intent, but when we look at sentiment analysis, we're looking at, hey, was this person happy or sad? Were they being facetious? Do they have sarcasm? And to do this, we have to have all that underlying how we got here. Hey, we have a vector, and then from the vector we built from here, and so that is not what I'm looking for. There we go. I just copied over the questions, so there. Again, when I try to bold these two questions, those are really the ones I care about. What would you use, or how would you use this in a business application, or how would you apply it in research, or how would you use this, to make the world a better place? How would you use this to get to goal? How would you use this to solve a problem? So that's the number 4 question. And number 2 is find an example of where semantic search works better than keyword search. And I have great examples of this. I have a whole program I wrote just to do semantic search for papers. So let's just go over the questions in general, then we'll get to everything, the code. So what makes two sentences similar according to the model? Well, the model doesn't really compare words. This doesn't compare words anymore. It compares meaning. Okay, it's an embedding model. When a sentence gets, converted to numbers, transformers look at all the words around it. And it goes into a single dimension. It goes into a single big vector. The two sentences that land close together in the vector space, they express the same idea. I love you very much. You are the apple of my eye because of my love for you. Things like that. This is the worst restaurant I've ever eaten at. I'm never eating here again. I got food poisoning. See, they're very similar sentences. And instead of just having, single words, like happy and joy, and we saw some of the downfalls with that, we can now move it past that. We can take chunks of sentences. This movie made me cry. I was sobbing and absolutely heartbreaking. So if I said, hey, that movie was so good, it's absolutely heartbreaking, it's hard. It's harder for a vector to understand that. When we start doing embedding and we look at the whole sentence, this movie was so great, it was absolutely heartbreaking. That means it's, a great movie, a motivating movie. I guess that goes to number 2. And that's an example where semantic search works better than keyword search. Now, as with everything else I try teaching in this class, nothing's perfect. So how does this fail? Sarcasm. Oh, great. Another Valentine's Day movie. Just what I was looking forward to. Oh, great. Another Universal Studio. What's it? The Marvel one. They have like 10 of them. Oh, great. Another, I don't know what it is. Marvel Studios movie. Oh, great. Another Star Trek Academy. Oh, great. Just what I need. Another great Star Trek movie to waste my time. And my struggle on that. Maybe sometimes domain mismatches. Maybe non-English movie titles. And then finally, to just kind of go over question number 4, how would you use this in business? Well, we talked about monitoring kind of radio waves and YouTube. Well, we could look at that now and say, when people are happy or when people are sad talking about it? Are they generally happy or are they generally sad? Or when they nobody leaves with comment cards, but when people leave a review, what are they really saying? This is part of my job at work. I have access to phone calls. I try to figure out, are they happy or are they sad? How can we prevent them from calling in? How can we prevent them from going to the hospital? How can we help them and give them the tools they need so they don't have to call us? I don't like calling an insurance company. I don't like calling a pharmacist. I don't like calling UNLV. I don't like calling people. Things should be somehow self-service. So how do we make that happen? How do we make the customer happy so we can retain them longer? So PDF instructions. Okay, so semantic search means you are not searching necessarily by keywords. So if you're saying, hey, I'm looking for a red Ford, and the model returns, hey, a red Chevy, that could be a semantic search. Zendesk reduced ticket resolution times by 40% by using semantically similar terms to match incoming tickets with past solutions, even when customers describe the same problem differently. Google processes 8.5 billion searches a day. I'm sure they process more than that. The traditional keyword matching fails when users search laptop won't turn on, but the solution article says computer not starting. Resume screening. LinkedIn matches job descriptions to candidates using sentence embedding. 5 years of machine learning experience matches extensive background in ML and AI. And this was that little visualization I made for cosine similarity. We can see these two are more closely related than this. And that's just a takeaway. Don't worry about the math. This is not a math class, not a CS class. I don't care if you know the math or not. Cosine similarity, you need to understand that, hey, two people heading to California probably have more in common than a person heading to Elko. Okay. I love the movie was absolutely fantastic. I love this film. It was great. 0.89. Very different words. Very, very different words. What one word's the same here? The movie was absolutely fantastic. This movie was terrible and boring. Now, these two sentences are closer in terms of verbiage, but opposite sentiment. This is what we're trying to get at, because this is how humans are. This is the way and why we talk. We don't talk with perfect clarity every time. Okay, so let me download. Oh, download there. Download. Let me switch over to. Let's try anti-gravity from Google. Why is it not showing up? For 1 second. Okay, anti-gravity class, anti-gravity. So we don't have the Colab extension on here. Colab install. What else don't we have in here? Install. Claude. I don't know if I really need Claude. What else might I need here? Notebook. I don't think I need that. Let's think about anything else. I'll throw this one on and Google stuff in there. Firebase. Okay. And remember too, when you install these extensions, just know that they could be bad if they're made by some, you know, crazy person that wants access to your computer. You know, like this one, I have no idea what this is, but the guy that publishes PKKKKK. So, you know, just be careful. You know, when I install things, I install it from either Google, the actual Google company, or from like Microsoft or Claude. I try not to install any extensions that aren't from like the real companies. Let me get my notebook loaded here. Okay. Um, Downloads work. Fix embedding. Okay, remote decision, open. Let's just ask this. What do we have here? What can I do or learn more relating to this notebook? I want to figure out how to apply sentence embedding to a real world problem in 2026. We just okay, so now with this, remember with Colab, I'll probably have to re-initialize it. Okay, there we go. So it's initialized. It wants all types of permission issues. Allow, allow. Allow. Give me 1 second to authorize everything. And basically what you're going to do is get, yes, you may now return to the editor. So, you know, it asks, hey, do you want to sign on? I'm like, yes. So, so we just load a model, do some type of text encoding. I'm just looking here. This is going to look at different movies and try to figure out what's similar. Okay. And then looking at kind of part 4, this is a semantic search, a similarity search. This is what is becoming more and more important in every life because people don't want to search for just plain keywords. They want semantic search. Okay. So, you know, if we're looking for movies with a villain wins at the end, I guess a bad guy wins at the end. If we use a keyword search, we'd have to know the name of the movie, or, you know, like bad guys always win if that's the name of a movie. However, with semantic search, that's not necessarily the case. You know, we can identify movies similar to that idea. Now, this compares 2 titles together. So, easy peasy. So I'm just going to hit run all. I'm going to let it run for a second, and then, you know, I think if I want to get this data set or different data sets, I'm going to let it run, and then I'm going to see the results, and then I'm going to find another data set. Give me 1 second. Okay, let's just see what we have before we move on to a different data set. Okay, just headed a couple rows. No, don't forget to save your work. I forgot to save my work up here, so I had to just save it and rerun it. But anyway, so let's dig in here a little bit. We can rerun it all if you want, but it should be mostly saved. Nope, we run it all. And then we'll find that other data. I found an Amazon data set, which I'm going to use here. 2, 4, collab 2, 4, H. Okay, I'm just rerunning this all. Like I said, that's the nice advantage of having collabs is you just rerun it. So I'm going to rerun it, and then we'll talk about it. So I just didn't save it. Okay, I think it's mostly loaded and done. So let's look at this. So this is just one of the models that we use right here. It's, a pre-trained model, meaning someone else, grabbed a bunch of data and trained it so we can use it. That L6 means I think there's 6 layers, 6 transformation layers, if I remember. The V2 is just the second version. There might be a newer one. It's just one that I know of. Again, I'm just using the data that I gave myself. But we can always deal with that later. We can always find a different data set. And this movie was absolutely fantastic. I love this film. It was great. Okay, these sentences have the same meaning. Now, if you notice, these two are not. The bank is by the river. I need to visit the bank for a loan. The term bank is very different in these sentences. The meaning, the context is different. So this right here would have failed in what, homework 4? The the word to vec. Okay, number of embeddings, number of dimensions, sorry. 384 dimensions. The number's right here. Okay, so right here, this is going to cut the text down to 512 characters. This is just so we don't run out of memory. That's really the only reason. I can't select this thing. That's the only reason that we basically do this. 512 is just like I said, we're probably going to expand it. But I'm just saying that's why I cut down to 512. Yeah. Okay, so what this is telling us right here, we look at sentence A and sentence B. How similar are they? I mean, we all know that this movie was absolutely fantastic. I love this film. It was great. Those are very similar sentences. I mean, as humans, we understand that. The cosine similarity is they're similar. They're going in the same direction. However, the bank is by the river and I need to visit the bank for a loan. Those are two very different concepts. Conceptually, you're doing two different things. You're talking about an inert bank on a river, mud, and then you're talking about a physical place where NER would probably, pick up both of these. Word to vec would, treat them the same, but we're doing this different. And look, the similarity is 0.5, much, much lower. So it knows that they're different. Here's a heat map here. So, when people say, oh, I never said that, but his intent was the same. So now what we can do is we can look at posts on YouTube, on Twitter, on calls that we convert to text, emails, and we see what's similar and what's not similar. We know that, as before, 0.82, these two are similar. I love this film, and this film was absolutely 0.82 right there. 0.82. This kind of just shows us how things are related. I need to visit the bank, and this film was absolutely fantastic. They're not very related. And again, you can put your own sentences in here and play around with it. You have to put them up here. But now you can visualize what is similar and what's not similar, not based just on keywords. And this is a very tiny, small, conceptual idea of what Netflix does, Amazon does. Everyone does this in order to make recommendation engines that work better. This is a method, function to search in the data set. So what we're going to search for is here. Movies with a surprising plot twist. Weak plot, predictable violence, only semi-interesting characters, looks like blah, blah, blah. So not very good right there. Movies with a love story, but someone dies. Much closer. This movie tells a lot about love stories without any coherence. A movie with a killer. Killer wearing a mask and running in the woods. Again, you can change this to look for more. You can do a lot of things, but this is basically how Amazon, Pandora, just name anything that does more than just a real stupid search engine like a keyword search. This is how it works. You have now designed or have code or have an understanding of how to create a semantic search engine. Get rid of this. I didn't even really read that. But winning. You know, this search function never looks at the words in the query. It does not look at any of these words. It doesn't look at any of these words. Okay. It doesn't check if killing or wearing a mask or woods is actually in there. It compares my intent. It compares my meaning. The meaning of every other review. Now, this is a small sample. If we had like, millions and millions and millions of reviews, we had something much bigger, we need a different database. We need a vector database, pinecone. Okay, these three queries right here, these three strings, sentences, we want to know whether the model can handle a nuance. The score here is still really low. And not like, it's not 0 and it's not negative, but still. And 0.5 is not bad. So I should anchor on that, because remember, if it was negative, there's a range in these scores. So 0.5 is not bad. It's just not, 0.6, it's not 0.8, things like that. Yeah. Okay, so let's look for films I didn't enjoy. That's probably one of the more important parts of the homework. Demonstrates why sentence embeddings matter. Okay. The films I didn't enjoy, then so hey, what is wrong with Walmart? What is wrong with Amazon? What's wrong with this product? But what would be the problem with this keyword is that it would hit on the joy, and you'd find a lot of false positives. You remove stop words, you may get rid of that. But with semantic search and cosine similarity in vector databases, and now LLMs, more or less, you know that we're looking for bad movies, bad reviews, bad problems, issues. You know, if you build a semantic search system, a recommendation is in something, customer support tool like, what was it? I can't even think of the name of it. It was, it's on here. That company that had a 40% ticket reduction. I don't know if it's Salesforce or CRM or whatever it was. Where's it at here? Right here. Right, where's it? Right there. Sorry. That we want things to be real, because in the real world, transcripts, text, Twitter, it's super messy. Yeah, it's pointless to sometimes try to do spell checking. Sometimes it's pointless to a lot of these text cleaning processes because the data is just so dirty. I have a great example. It's just, you know, I can't share it right now. It was on Reddit yesterday. Let's see what else we have. So yeah, that's a bulk of it. I guess if you want, we can try a different data set. You know, the one I was going to play with. Let's see how we at time. Ooh, 20 minutes. So let me end this video. But there is, you know, if you want to try a different data set, what you can do very easily is just do some Amazon reviews. So I just really quick changed it to an Amazon, it's Amazon reviews. That's all I did. And you have to, I had to change the name, so it was text. I had to change the review. I also loaded 20,000 reviews. I had to cut it back down to 512. But here, this product is amazing, totally worth every penny. Great value for money. I'm really impressed. We go through here. Now look, so here's the semantic similarity again. And we can see the sentences there are, and right up here. Shipping was fast, but the item arrived damaged. Delivery took forever, but the product itself was great. The battery doesn't hold a charge anymore. The battery sucks, so it should say. So we can kind of go down here and look at the heat map and now understand what's going on. So, like I said, I encourage you to test and play with different models or different data sets. Because now, I mean, with this notebook, we have the tools to create a semantic search. So, you know, we know, hey, if I like this movie, I might like this other movie. If I like this product, I might like this other product. I use something like this in a PhD to find papers that nobody else was really using. So part of my PhD, there was the word Parkinson's, but maybe it's Parkins without an S, or maybe they spell it differently, or maybe they diagnose it differently. So there's a lot of applications for this. Let me know if you have any questions. Have a great week.